Since I haven't had an original idea in about 20 years, in fact, probably ever, I thought I'd re record an old seminar from about 20 years ago about wealth condensation as a zero range process, a ZRP. It's such an old seminar that the Harriet Watt crest here up in the corner is a couple of iterations back from our current one. And this is based on a Phys Rev E down here, with various co-authors indicated here. When I originally gave this seminar, it was pointed out to me that my notation was slightly incorrect. I'm not really talking about a zero-range process as a model for this wealth condensation. I'm talking about a zeta-earn model, the steady state of the zero-range process. And this was pointed out to me by Claude Godrèche, who's an expert in such matters. So the plan. Firstly, apologies. This is really going to annoy any economists who happen to listen in. Very unlikely, I know. It's really an exercise in relabeling from a statistical mechanical model to a rather unrealistic toy economy model. Nonetheless, I'll still try and attempt to set it in an economics context. I'll talk about the observations of Pareto for wealth distributions for rich guys, and Gibra rather later for distribution of wealth, income, sizes of firms for more moderately sized firms or for less rich people. I'll talk about the sorts of models that might give rise to these observed distributions, and then I'll talk about the situation where there's a finite total wealth in our toy economy, which isn't the case with some of the other approaches to obtaining these distributions. And the model that we'll use in the case of finite total wealth is precisely this zero-range process, or rather zeta-earn model, if you prefer a different TLA. In fact, there's a four-letter acronym that we'll talk about briefly as well, the ASEP, or asymmetric exclusion process, which is related to the zero-range process. The model that we're going to use for our toy economy is basically distributing balls, if you like, money or wealth, into boxes, different actors, different people in the economy. And there'll be a certain probability for each box to have a number of balls, to have a certain wealth. And there'll also be an overall constraint on the wealth in the economy. And it's the interplay of these two things that give the interesting behavior in the model. So firstly, not a ZRP, but a ZUM. Let's talk a little bit about the economics context. The observation is that the rich really are different. If you look at a distribution of wealth, whether it's income or other forms of wealth as well, typically what you see is that the majority, most of us, follow a log normal distribution. But there's a tail for the very rich guys. Bill Gates, one of the good rich guys, or even the baddies. The probability of wealth in the tail doesn't go as a log normal distribution, it goes as a power law. And by convention, this is denoted as 1 plus alpha, inverse power law here. And the guy who first observed this was Pareto, way back in 1897. He looked at, amongst other things, personal income for the wealthy and observed this power law distribution. The alpha is named after him. It's called the Pareto index. And empirically, this is found to be between 1 and 2 whenever you have a look at such distributions, the tails of such distributions. It took a little bit longer for people to get interested in the rest of us rather than just the rich guys. And Robert Gibra, formulated his law in 1931, which stated that the wealth for the majority of folk followed a log normal distribution. In fact, he had a law of proportional growth, both for people's incomes and for the size of firms, which resulted in this log normal distribution of the wealths or income of firms and such like things. There's another index associated with this, beta in this case, which is related to the variance or the standard deviation of this log normal distribution, and that's called the Gibra index. So to summarize, rich guys power law distribution of wealth. The rest of us, log normal distribution. And the people in question, here's Pareto with a magnificent beard. Here's Gibrat, looking very Jean-Paul Sartre with a pair of severe specs. And the other name that's associated with observed power laws for distributions of things in real life is Zipf. Gibrat was a well-known engineer. He became a minister in the Vichy government and as a result was prosecuted at the end of the Second World War. But after the war, he carried on with his engineering career, became interested in both tidal power and nuclear power. So he had a long and distinguished career as an engineer, possibly a slightly less distinguished career as a politician. And just to show a couple of examples of both a log normal distribution and a power law tail, let's have a look at wealth, or rather income, for the Japanese economy. The income's in millions of yen, so it's probably slightly less than you might think, for 2 different years. So this is the P of W, the probability of having a given wealth, and it's a log plot. So for most folk, this is following a log normal distribution, but we can see that it peels off into the tail, where it becomes a power law for the richer. And this is replicated in later data from Japan. 1995, what happens is people are earning more, but there's still a log normal distribution for a considerable chunk of the curve. And then for the rich, it becomes a power law here in the tail. So this is a fairly robust observation. Log normal lower down, for rich folk, a power law tail. How might you arrive at such distributions? You can get a log normal distribution from a multiplicative stochastic process, an MSP, yet another TLA. So you've got some amount of wealth, x of t. So this will take as fractional wealth between 0 and 1, and it gets multiplied by some stochastic amount, a of t. And I carry on doing this over different time steps, and I find that I end up with a log normal distribution for the x's. It's harder to pick up the power law tail, but I can tinker with models like the multiplicative stochastic process. I could stop the drift to 0, minus infinity if I'm taking logs, if I put in a poverty bound xm. In effect, this is a reflection. And in that case, for some xm between 0 and the wealth that I've got at time t, I pick up a Pareto index in the tail, given by this. Remember, xm's a fractional wealth, so it's going to go between 0 and 1. I can achieve a similar effect by also putting additive noise into the model. So I can generate both a log normal distribution for the bulk and a power law tail by tinkering around with simple models. I'm going to look at a model or a class of models in particular with individual agents, and this was originally formulated by Bouchot and Mézard. They wrote down a differential equation for flows of wealth. So the JIJs represent trades between actor I and actor J in the economy, agent I and agent J. And there's also a stochastic term. So eta is some sort of stochastic noise. We could take it to be Gaussian, for instance. And what they did was they looked at a mean field version of this, where every agent in the economy interacted with every other agent with the same coupling J. There are other equivalent models or very similar models. There's a generalized Lotka-Volterra model that was investigated by Solomon et al., where you can obtain rather similar results. But we're going to concentrate on this one at the top. So in the mean field solution, all of the couplings Jij become J divided by n. We have a look at the mean wealth. The eta, the stochastic noise, this can be taken to be the same for all of the W's. And if it has a mean m, variance sigma squared, we can express this differential equation in terms of the normalized wealth. so a fractional wealth between 0 and 1, as this. And it's possible to work out what the steady state of this equation looks like. And the steady state is precisely a power law distribution, damped by an exponential, which looks like this. In the case of the simplest model that we've looked at, the alpha is greater than 1, this exponent, but it can be twiddled. So this would fit in with empirical observations, but for the purposes of the toy model, we'd like to be able to make alpha both greater or less than 1. So we can add additional terms to the differential equation, or we can modify the assumption that everybody is trading with everybody else at the same rate j. If we do this and obtain an alpha that's less than 1, we need some indicators for seeing what's going on with the individual wealths. One possibility is to have a look at a partial wealth. We can rank order the wealths of the I agents in the economy up to some given wealth n. That's called Sn. Another useful indicator is the inverse participation ratio, which is given by the sum of the squares of the individual relative wealths, and we sum over all of the agents in the economy in this case. The Y2, the inverse participation ratio, acts as an order parameter for wealth condensation. It can pick up if one or more of the agents has picked up an extensive amount of wealth, if they're hoovering up an extensive amount of money from the economy. In that case, the Y2 will be non-zero. And we can arrive at a situation like this by twiddling the alpha in the model. If alpha is greater than or equal to 1, the mean wealth is finite. Remember, the alpha was given by a combination of the couplings and the variance in the noise. If we added additional terms to the differential equation and made the alpha less than 1, the Y2 becomes non-zero, the mean wealth becomes infinite, and somebody picks up an amount n to the 1 over alpha of the wealth. So what we see is, if there's a non-integrable tail in the wealth distribution, somebody is guaranteed to pick up an extensive fraction of the wealth. There's a wealth condensation. So it's a slightly strange mechanism. We've got a non-integrable tail in our distribution of wealth, and somebody's hoovering up that amount of money in the tail. A question that you could ask is what happens with a finite economy where you don't have this non-integrable tail? And this is where we're going to use a balls and boxes model to investigate the behavior of such an economy. So let's formulate our model. It's not really a zero-range process because we're looking at the steady state. It should be a zeta-earn model. So we've got an economy where everyone is rich. So everybody's wealth, bare wealth, if you like, the probability of getting a certain amount of wealth in a given box follows a power law. In addition to this, there's also a constraint, this delta function constraint, on the total wealth in the economy. We're not allowed to print money. So there's no quantitative easing in this toy model. We're not allowed to buy up assets, put money into the economy. And this Z is an appropriate normalization. So there are N rich guys. The total wealth is W. There's this constraint as a consequence. And there's some sort of power law distribution for each one of these N rich guys or boxes in the model. And we're going to have a look at what happens in the limit where both W and N get sent to infinity, but in a fixed ratio. So rho, W divided by N, is a wealth density in this model, average wealth density. And this steady state distribution is the steady state distribution for a zero range process. So in a zero range process, you've got a bunch of boxes, sites, and a bunch of balls. The hopping rate of the balls from one box to another, so I've got them going just to the box alongside, it could in principle be to any of the boxes. The hopping rate is given or depends on the number of balls in a given box. It can vary. This zero range process at the top here can be reformulated as an asymmetric exclusion process. So the sites in the asymmetric exclusion process become the balls in this case, and the number of balls in a site becomes the number of spaces between the black balls representing the sites. And the hopping rates in this case are reversed. They depend on the number of spaces to the left of a given ball. The steady states of these two models are identical, so there's a mapping between the two of these. You might wonder, given all of these hopping rates, what the steady state distribution looks like for both of these models. And it can be determined exactly. You can show that the probability of having Q balls in a given box is given by this product between 1 and Q of the inverse hopping rates. So this is an exact relation. And I can invert this to get the hopping rates given the probability of getting Q balls in a box in the steady state. So I can tune these U's to pick up a particular P of Q. I'm going to solve the model in the limit of the W, the wealth, and the N, the number of boxes, going to infinity in a fixed ratio ρ, density of wealth, by taking a saddle point solution. So we do that, first of all, by exponentiating the delta function that gives me the constraint on the total wealth. And I write the W in this case as ρ n. Doing this allows me to write the P's here in this form. So this gets absorbed into this as this product factor. And now I can exponentiate this thing, which is multiplied by n, to get this factor in the exponent. And this is set up perfectly now for doing a saddle point expansion, because there's an overall factor of n, which is multiplying the thing that I'm interested in. I'm taking both w and n to infinity. So I take this n to infinity, and the k that's written down here, I lambda, is a Fourier transform in effect of this probability distribution, a discrete Fourier transform, or rather the log of a discrete Fourier transform. So I can now work out what the saddle point solution for this looks like. So the term in the exponent takes this form, and the sigma star of ρ appearing in the saddle point solution is a solution of this equation. Remember, the k is given by this, so I can differentiate it explicitly to find k primed. And the z of w and n, this partition function that I'm trying to calculate in the saddle point approximation, this normalizing factor, is given by an expression that looks like this, as n tends to infinity. Let's now consider the behavior of the sigma star and ρ in this expression, which is giving us the saddle point solution. What we find is, as we increase ρ, sigma star decreases, and it gets to 0 whenever the probability of balls in a given box is a power law distribution before ρ gets to infinity. So at some critical density, sigma star will have gotten to 0, and that critical density is given by this expression. Sigma star is 0 up here. I solve this for ρ, and if I've got a power law distribution with some exponent for the P of Q the probability of getting Q balls in a given box, this critical density is given by this ratio of Riemann zeta functions. So that's where this notation or terminology of a zeta-Ern model comes from. You've got power law distributions. Summing these things up will give you Riemann zeta functions. So a question that you might pose is, what happens whenever I increase the wealth density beyond this critical density? I can still do that. My saddle point solution has broken down. Something must be going on to rescue it. To investigate this, we can have a look at the effective probabilities for balls in boxes, or for a given amount of wealth possessed by a given agent. You start out with a P of Q as the probability of having wealth Q for a particular agent in the economy. But I have to take into account the effect of the finite total wealth as well. And that's done by using this ratio of the normalizations. So if there are Q balls in one particular box, that takes Q away from the wealth and 1 away from the number of boxes. And I have to put this ratio in to make sure that the sum of all the different probabilities, given the constraint, still adds up to 1. And I can use this in an exact calculation of the Z of W and N. I can write down a recurrence relation with this starting condition. If there's only one box with Q balls, the probability is going to be P of Q. When I start adding boxes and balls on top of this, I can write down this recurrence relation for n greater than or equal to 2. And that gets me the Z. Once I have this, I can think about what the saddle point solution looks like. In fact, what the solution looks like exactly. And if I use the recurrence relation for finite n and start looking at larger and larger n, what I see is this. So let's say a little word about the parameters that we've put into this graph. Firstly, I take a power law distribution for the wealth in the individual boxes. This is before we take into account the constraint from the finite total wealth. In this case, 1 plus alpha is equal to 4, the power law. So the critical density at which the saddle point solution breaks down is given by this ratio of zeta functions. It's 1.106 ... What I've plotted out here in the graph is pi of Q, the observed distribution, probability distribution of getting Q balls in a given box. And I've increased the number of boxes, the number of agents in my economy, from 128 through 512 to 2048. And I've taken the density, rho, to be 2, which is bigger than this critical density here. And what I see, instead of simply the 1 to the Q4 power law, these are log-log scales, so the power law appears as this line, is that the distribution acquires a peak at large Q, which is increasing with the size of the system, more or less linearly. So this shows that the saddle point solution is rescued by a condensation of an extensive number of balls in a given box. If you like, there's permutation symmetry breaking once you get to the critical density. Beyond that, because the smooth saddle point solution no longer works, we pick up an extensive number of balls, in this case increasing apparently with n in a given box. That's what this peak represents. We can do this slightly differently. Let's take a fixed number of actors, agents in the economy, a fixed number of boxes. Let's take the same distribution for the individual wealth initially, 1 over Q to the 4th, And let's plot out the observed distribution pi of q, which takes into account the constraint on the finite total wealth. And instead of changing the size of the system, let's scan up through the wealth density. So we're increasing the wealth density here. Initially, we get what we expect. There's a damped version of this power law. We've got exponential damping, which takes account of the finite total wealth. As we approach the critical density, it approaches the 1 over q to the 4th power. And as we move through the critical density, a peak develops, indicating the condensation of an extensive number of the balls in one particular box. So if we look at the expressions for the density, the critical density is given by this exactly. Or if we've got a power law distribution for the P of Q's, the expression that we used before, and the pi of Q, the observed distribution of balls in boxes, is the Bohr density, the power law, 1 over q to the 4, plus a delta function expression that looks like this, representing the condensation of an extensive number of the balls into a particular box. So one guy has ended up with an extensive chunk of the total wealth in the system, simply as a consequence of the density, the mean density of wealth, increasing above this critical value. It's a result of the competition between the individual probabilities and the finite total wealth. Non-condensation, so if we're below this critical density of wealth, there's a damped power law. That's what was expected from the solution. That's what we see for the pi of q. At the threshold, the inverse participation ratio, this expression that we defined from the individual wealths, the squares of the individual wealths, changes from 0 to this. So W over N is the rho. Rho critical is the critical density given by the ratio of these zeta functions. As rho increases past rho critical, rho minus rho critical squared becomes the value of Y2. It's acting as an order parameter for the condensation. It's an indicator of when all of the ball, or an extensive fraction of the balls, has condensed into one of the boxes. So, to summarize what we've seen, in this model of an economy composed entirely of rich guys, where there's an inverse power law probability of having wealth Q and a constraint on the total wealth in the economy, when the mean wealth increases past a particular critical value that's determined by the power law, there's a condensation of wealth. It's simply there in the model. We might think of tinkering with our toy economy. So if you've got a power law, inverse power law for wealth, a good socialist chancellor, John MacDonald for instance, might decide to increase the inverse power as a way of suppressing large wealths. Let's suppose that we started with a value of the wealth density rho that's below the critical threshold in some economy. If you look at the expression for the critical density of wealth, where the condensation takes place, you can see that increasing alpha decreases the critical density. So the plot of the ratio of the two Riemann zeta functions looks like this. For increasing alpha, rho critical decreases. So if you're at some particular value of alpha and you're below the critical density, and your socialist chancellor decides to soak the rich by increasing alpha, that might actually push you from the uncondensed phase of the model, where the wealth is spread more evenly, into the condensed phase. So bizarrely, increasing alpha decreases row critical and pushes you into a wealth condensation. So even though you thought your physical changes were improving the situation, you could end up condensing the wealth into the pockets of one of the rich guys in your economy. It's not meant to be a realistic model, but it's the effect that you see in this case. So just to finish, why did I get interested in this sort of thing, coming from a theoretical physics background? I was working on simulations of both two-dimensional and higher dimensional quantum gravity, where you bolt together triangles in 2 dimensions or simplices in higher dimensions to try and represent dynamical geometry, and you allow these to fluctuate either by adding additional triangles or simplices or by flipping links in the triangles or simplices. And what tends to happen, particularly in higher dimensional versions like this, where you've got simplices rather than triangles, is that you don't get smooth geometries. You end up with things that look like branched polymers. And depending on the parameters in your model, these branched polymers can undergo a condensation into a geometry that looks like this, where you've got one vertex in your discrete geometry that's connected to just about everything else. And there's a direct mapping between the polymer model and a balls in boxes model. So this geometrical condensation is what you see in the simulations as well. And it's simply because this corresponds to a